Okay, so today we're doing Euler's method, and this is a BC calculus topic. Okay, so in example 1, we're given the differential equation dy over dx is negative x over y, and we know that y of 0, that means when x is 0, y is 4. So to approximate y of 4 using, when x is 0, and it told us y was 4, we don't need to solve that, using a step size of delta x is equal to 1. Okay, so why we're given this information and how Euler's method works is basically according to this diagram. So let me pause this so I could draw out the diagram. Okay, so here is how my diagram is going to be formed. Please bear with me. All right, so we know at 0, 4, it's like our given value over here. And so we kind of use a step size of 1 here, all the way over, to figure out what our approximation is. And so the actual value could be near there but not exact. And what we do is we use slopes to kind of approximate where that is. And we just keep using different slopes along our curve. I'm going to try to draw one in here. Okay, and it should actually be going out to 4. With this differential equation, we can actually solve this one. You don't always have to solve it. And when you do, we end up finding C and writing our equation. It happens to be a circle with a radius of 4. So that's why, as I started to draw this out, it looks very sloppy. Kind of like I was drawing hair on a stick figure. But I was trying to make like a quarter circle here. I didn't exactly make it because I'm trying to squeeze it in with the slide and everything. But let me see if I could trim that down. Basically, you're getting the idea, hopefully, that we're using slopes of our tangent line to kind of get the approximation as x becomes 4 out over here. So we just keep on doing that, and that's why it says like delta x is equal to 1. That actually means our step size is 1. Okay, so there's actually a pretty lengthy procedure for doing this. But as you do this, it'll start to make more sense with the diagram. So let's start working. Okay, so our initial point, we call it x sub 0, y sub 0. This was 0, 4. Okay, and our slope, if we plug in 0, 4, we get 0. Okay, so if we were to write the equation of the line using this information, I'm going to use A, because this is going to change as we get to more points. It's not going to stay y sub 0 and x sub 0. I'm going to change that subscript to an A. We find that y is equal to 4. So we're getting y of 1 to be 4. Okay. Next. Okay, so that's what we were getting like at the first line that I was drawing. Okay. So we're going to do the next point. So then we're changing our subscript to 1. And we got 1, 4. Okay, step size was 1. That's why we went from 0 to 1. Okay, that's 0 to 1/2. Anyway, so we're getting 1, 4. So if we plug that in to get the slope into our differential equation, we're getting negative 1/4. So if we plug this in, and you can see why I'm also not using x1, y1. we get the equation y equals negative 1/4 x plus 1/4 plus 4. So that's going to end up becoming y equals negative 1/4 x plus 17/4. Okay, so now we're going to do the next value. Remember the step size is 1, so from 0 plus 1, we get 1. From 1 plus 1, we get 2. We're going to find out what we get when we plug in 2. Oops, that was supposed to be a plus sign. Where am I going? So we end up getting y of 2 to be 15/4. Okay, you can keep it as a decimal or a fraction. That does not matter. Okay, and we're going to keep doing this until we get to 4. Okay, so let's go. I'm going to erase this part up here and do this again. Okay, so our next value, our next point. All right, and as you're kind of doing this, you're getting the slope, you're trying to imagine that line that I was drawing into our very weird looking curve. Okay, so our slope this time is negative 8/15. All right, we know the formula, so we don't have to pretend we don't know it. So we end up y is negative 8/15x and 16/15, and I'm adding over the 15/4. So it's going to leave us the common denominator of 60. So this does become lengthy. If you need your calculators, that's okay. All right, so our step size is 1. If we add 1 to 2, we get 3. So I'm going to plug in 3 into my equation here. I'm running out of space. I can get in there. So we end up getting y of 3, and that is 193/60. Okay? So now we need to use this, okay? And I'm going to erase some more down here because I need more space. All right, I'm also going to change color too. Okay, so this is our given information. And we're going to use the slope. And our slope becomes this large fraction here. Don't be scared. We can use that. Here it goes. So it's very repetitious, but in the end, we're hopefully getting the idea about how we're using this to approximate our value. All right, we're going to get a large denominator here if we combine length terms. So, I mean, if we have a common denominator. So instead of doing that, I'm just going to start plugging in 4, okay, which is our next value after 3. So if I plug in 4, I'm going to use my calculator. Figure out what this is. All right, so if I use my calculator, I end up with this number that's not going to convert to a fraction. My calculator gives me 2.2840218. Whew. So we're going to approximate this, okay? So we're going to say that x sub 4, y sub 4 is approximately 4, 2.284. Always approximates 3 decimal places. Okay, and if you end up getting this as your answer. Okay, that means y of 4 is about 2.284. And believe it or not, that's what we're looking for using Euler's method. Now you may be thinking that we kind of knew from the beginning, because I told you it was the circle, x squared plus y squared equals 4. And I'm just writing this as a note. What happens in this particular case when we go to solve for y, and that's why we use this method, we may not be able to actually get your equation from solving the differential equation. We get 0. Well, we were saying it was 2.284. So Euler's method is off. It is used as an approximation, and our error is of approximately 2.284. So it seems like a lot, and what I'm saying here is that typically your step size isn't 1, it's usually less. I use 1 as the example because it's very easy to use. Usually your step size is like 0.1, okay? 1 is really way too big. It's a whole integer. So when you do have something like 0.1, it's easier to get a value that's closer to the actual than to have such an error, such a big difference off like this one. But hopefully you understand the whole method and the concept behind it to get our approximation. So good luck.